Okay, this is Logan Glantz. This is my regression module 1 for regression. We got a lot to talk about, and I keep running over time when I record these, so let's just go into it. What is regression, and why do we like it so much? Well, regression is when we use predictors, variables, to predict an outcome variable or a dependent variable, which we'll call y, right? And we really like it because even though it doesn't prove causation, it gives us a lot of informative data about the relationship between our variables, and it can give us a predictive model, which in the end is what we really want our data to do. Some caveats: there are a lot of violations to regression that we often make. For example, you're not supposed to measure any of your data with error. There should be no correlation between predictors, etc., etc. But this often isn't possible in real life. Data is messy. You can't measure it with error. And so what we do is we try to get the blue, or the best linear unbiased estimate that we can. So, and my theory behind regression and Friedman paper says pretty much the same thing, is that if you do your homework and you understand the theory behind not only what you're studying, but behind regression, you can use regression as a really powerful tool to not only show a relationship between the data, but even lead strong evidence towards your theory, even if it's causation, which regression can't show, but it can really lend a lot of strong evidence towards looking into whatever you're looking into. On the flip side of that, if you just take your data and force regression upon it, regression will give you numbers back, but it may not be the best tool. It may not be accurately showing you an appropriate picture. And so the important thing to do right here is how I make sure regression will work. The first thing you need to do is really focus on good experimental design. If you had a good experiment, you've done your theory, your model's not misspecified, you're not including redundant predictors, those sorts of things, you can use regression to show you a lot of really interesting, a lot of excellent things and trends in your data. And as long as you have that and make sure you interpret it right, you should be okay. Now, doing it right and interpreting it correctly is a lot more. It's like way easier to say, but if you understand it, you can really use regression correctly and very powerfully. The other thing you need to do whenever you're doing regression is to plot your data. I'll show you this later. When you plot your data, a lot of good things happen. Look at correlations, and then I always use the plot function in R or the 4-in-1 in Minitab. These show you a lot of things about your residuals, and you can make sure that they're all normal. So the first thing we're going to do is look at our data. Plotting your data shows you a lot of really important things. You'll see right here already what jumps right out at me is the correlation between x1 and x2 is extremely high. That's going to be a problem when we run our MRC. But besides that, plotting your data can show you a lot of other things that if you just ran the regression model and looked at the summary, you might not catch. For example, besides showing you the relationship between the variables and each other, it can show you if any of the variables are like binomial or in a metric you didn't understand. It can show you if your y variable isn't continuous. You can look at the relationship between your x and y variables and see if they're nonlinear or curvilinear. All sorts of things like that. So it's really important to plot your data and understand your data before you go forth and run stats on it and then claim that you've you have such and such effect. Down here is the correlations. Again, one of the assumptions of regression is that none of your variables are correlated. Good luck with that in real life. So what's important to do is understand what correlation means in terms of your variance and whether it's, quote, a big deal or not. So when variables are correlated, that means that there's some shared variance between them on y. And so depending on your sums of squares model, either that variance will be lost forever or it will be attributed to one of the predictors, whichever one you list first. So it's important to understand what that correlation means and how to deal with it based on your model. So if you look at it appropriately and make critical decisions based on your model, you should be able to mitigate the effects of correlation. Another thing you can do is look at the VIF, and if it's really high, then you might have a serious problem, and you need to look at perhaps finding other predictors. I don't really have time to go into the VIF, so we'll move on. This is the first model I'm going to run. This is just x1 regress on y, and right here, this little block of text gives us a ton of information. Really interesting stuff. So right here is the estimate for the intercept. Excuse me. What that's telling us is that when x1 in this case is equal to 0, that is the expected value of y. Alternatively, what this is telling us is this is the beta for x1. No, this is the b for x1. So what that means is that when you look at the regression equation, 1 unit increase in x predicts 111.37 increase in y. This is the standard error for our estimate. This is like a standard deviation for the expected estimate for our parameters in our model. What we do is we use these. It's basically how sure we are, right? I mean, you can create a confidence interval, and you use these to create a t-value and then a p-value. And basically what that's saying is it's telling us how likely 0 is to be included in the distribution, or I guess that confidence interval of our estimate. And if 0 is in there, that means that it's not significant. And so the p-value is telling us how likely it is that we actually have an effect for that variable, whether it's the intercept or the variable itself. We do, both are significant, so that's excellent. Additionally, down here is our R squared. This is a very important statistic. It's telling us how much our model is explaining the variance in y. So because we only have one predictor, it's telling us that x1 is explaining about 24% of the variance in y. This is the adjusted R squared, which is the same thing, except it's penalizing us for the number of predictors we use. As you include more and more predictors into your models, you're going to explain more variance. It's just what happens. So what this does is it penalizes us for including many predictors and gives us a more appropriate look at maybe what the actual variance we're explaining, rather than just kind of the mathematical trick of adding more predictors. So this is a really important statistic, and I'll just say that when, like he talks about in the Abelson paper, this variance, no matter how small, if it's significant, if your model's significant, I'll talk about that in a second. Even no matter how small this is, it's important. When you're systematically predicting variance in something, especially something you're interested in, every little piece is important. In the Abelson paper, he talks about baseball, and how skill is only 0.3% of the variance explained in the hitting models, which, okay. But we know that skill is really important, and when you're compounding it across many observations, that really adds up. I also want to say in that paper that I guess I was surprised that skill was that low, but when you think about it in terms of hitting over the hundreds of games, several hundreds at-bats that they have all season, if you're looking not at trying to predict a number at which they hit, but trying to predict, looking at their distribution of hits and trying to predict kind of like what they're going to hit at or above, shifting that entire distribution up, whatever, 0.3%, really compounds a lot, especially over the season. So as low as that number is, when you actually look at it in the scope of the entire population of hits for everybody, that small amount can add up. And so it's important, and that kind of relates back to this. Don't brush anything off because you're not explaining a lot of R squared, or your B is real small. Just because those are the case doesn't mean you don't have an informative effect. This is an F statistic. This tells us if our model is significant. If this p-value were not significant, that means that our model is basically non-informative and we need to devise a new model. So it's important to check your assumptions in addition. There it is. So we've already looked at the correlations and stuff. This is bivariate, so cool. This is residuals versus fitted. This is looking at our residuals across our predictor. So this should be straight line. That would mean that it's homoscedastic, but it's not. That indicates that there is potentially some heteroscedasticity. Generally, when I look at these sorts of graphs, what I'm looking for are cyclical patterns, right? So when you have like something cyclical, like what might look like a sine function plotted, or a megaphone of increasing variance, right? That's when you kind of indicate potentially that you have non-independence of residuals on your predictors, which is a serious theoretical concern. In this case, this sort of pattern indicates that variance just isn't consistent. I think this also might be due to the fact that we only have 20 predictors, observations in our model. So I'm going to take this information with a grain of salt. This is a normal QQ. It plots like on the bottom is like a perfect normal residuals, and on this side is what we have. So if they overlap completely, they should line up on the line. They don't. The paper you had us read on assumptions and how to fix them indicates that this sort of S-curve may mean kurtosis. What it also says is you want to make sure that what you're seeing in these assumptions is actually an artifact of your data, or is actually what your data is, and not just an artifact of either your data, how you've collected it, or how you've ran it. Again, in that case, I think that this sort of pattern may be just due to the fact that we have such a small number of observations. If you had enough more observations, over 30, that may indicate that some of this stuff will normalize just through observations. That it's probable that you just received such a small sample that this won't line up. If this were an issue, you have a lot of options. You can do some sort of transformation on your data. You can run a series of strange alternate regression models that take this into account with heteroscedasticity. You could just take a portion at which your variance is stable and regress that and just limit your interpretation to that. I like this one. So this plots leverage versus the residual standard deviation from the mean error. So what you're looking for in this is scary points that have high leverage and are non-normal error terms. So high leverage is okay, but also if they're an outlier and a residual for error, they'll be up in here, and this is Cook's distance, which indicates that a point is negatively affecting, or negative as in bad, affecting your model, and that it needs to be addressed. It may be an outlier, it needs to be removed. I did some other stuff here that I don't think we're gonna have time to go into. I did notice that if you if you make a x squared model, it actually predicts more of your variance. But if you look at the graphs, I just don't think there's enough points to say that the x value is curvilinear. Okay, so now what we'll do is run our MRC. And so what I've done is I've included all the variables x1, x2, and x3 from the data set together. And even though we know x1 and x2 are highly correlated, excuse me. And what you'll see here is that I didn't show you earlier, but x1 and x2 both have are significant when included in a model by themselves. But here, they are not, right? And so what happened there? Well, because they're so highly correlated, they have a lot of shared variance, shared impact on y. And apparently what R has done is not run type 1 sums of squares, because x1 and x2, neither of them are significant, which means that chunk of change where they're both covariate together influencing y has just been left out of this model. It's not been partitioned to either term. In like a type 1 sums of squares, because x1 was listed first in our model, x1 would get that variance and x2 would be non-significant. But in this case, each one doesn't have significant, isn't a significant predictor in this case. You'll see here also that x3 is not significant. So the only thing significant here is the intercept. So this isn't exactly informative, because none of our predictors are significant. This is just saying that I guess the intercept is explaining 27% of the variance in the model, which makes sense. It's not zero. Even look here, the adjusted R squared is very low. You're not explaining a lot of variance, and you have many predictors in your model. And you failed your F statistic here, which means that your model is non-significant. It's not informative. It's basically the same thing as having no model, right? Or zero. So you need to adjust that. I think that's all I got. I think I just eclipsed 15 minutes. I just want to say I think I spent 2 hours trying to record this thing. I would spend 15 minutes talking about this, and then I'd go again and I'd spend 5 minutes talking about the top, and then 15 minutes on assumptions. So I hope I got everything that we were supposed to include. If you have any questions on my ability of understanding this basic regression, I would ask you not to hesitate to speak to me, and we would figure it out from there. But alright, have a good Thanksgiving break, and I will show up bushy-tailed and bright-eyed for regression when we come back. Okay, wow. Final add-on to this video. I forgot my Durbin-Watson. I promise I test for autocorrelation between predictors, which is when multiple predictors are correlated with the residuals, which is not good, as you can see here for my bivariate model. Non-significant. A good thing. Okay, that's it.